So we begin this course with a topic that is kind of interesting. Right there in the text in chapter 7, they even have I think it might be a little sentence or paragraph where it talks about how maybe we didn't really need a special chapter for shafts. Right? That's our first topic that we're going to look at. More or less says you can take the methods that were outlined in chapter 6 for fatigue, and it doesn't take a lot of extra thinking to just apply those methods to the shafts that we will start to analyze here. But I actually think this is a great place to start with this course, because a lot of you have been through a summer now and may have forgotten a lot about what you did in chapter 6. And so it gives us a chance here where we can go back and do a little bit of review and see how some of the stuff that you learned back in chapter 6 now applies to a specific type of component known as a shaft. Shafts are typically pretty simple in terms of, they're usually just usually kind of long, slender member. They are designed to where they typically have to carry both a torsion load a lot of times, as well as a flexural load at the same time. And then sometimes they also carry an axial load, so they can sort of have this combined loading type of a scenario on shafts. And they are in a lot of different kinds of machinery. And so that's another reason why we might want a special topic where we specifically talk about shafts. So rather than get into a lot of, sort of generalized lecture, what you will find is that in this course, more often I tend to jump right into an example problem, and I try to talk about the more general cases as it comes up in the context of an example problem. One of the reasons I do that is that we have a lot of material to cover in 30 meetings, okay? And since we have so much material to cover, I have to be very selective for each of my little hour and 15-minute chunks with you. I have to be very selective about what I do, and I think this is one of the most cost-effective, cost in terms of time, effective methods of doing it. So, with all that said, this example is for what we could call an intermediate shaft. That's kind of a more formal name for it. In a lot of contexts, someone might refer to this as something that's called a jack shaft. All right. The idea here, this happens a lot in machinery. You may have a source of energy somewhere, and you're trying to transmit that energy somewhere else, and you may have to first transmit that energy from whatever your source is into some other shaft. And by doing this is one way that you can do things like apply mechanical advantage. And there may be other reasons why you might want to do this as well. But this is an intermediate shaft, and you might be able to tell by the picture that I'm trying to imply that this shaft might have maybe a belt or a chain applied to it in two different locations, two different belts or chains at two different locations. Okay, so over here I have a pulley or a sprocket that may have a belt applied to it. And then I have another one that's down here, okay? And this is kind of the nature of that intermediate shaft. I'm trying to be somewhat simplified as far as how I show it. On the left there you see the detail of the dimensions of this shaft, okay? One of the things that happens whenever you have a belt or chain applied to something is that there's going to be a difference in the amount of tension on one side of the belt or chain relative to the other side, all right? And it doesn't always have to have zero tension on the looser side, but it can. In some cases, you will see examples of this where there might be zero tension on the looser end of the belt or chain that might be applied. And so that's what we're going to assume is happening on this one, is that we have all of the tension being applied on one side of the sprocket, and that's a 70-pound load that's being applied right there. Okay, reacting against that so that this thing rotates at a constant speed. I should have probably put that up here, but I'll write it now. Let's say this is experiencing a constant speed. If it's experiencing a constant speed, then that means that there is no acceleration of the shaft. And that means that if we, for instance, summed moments around the axis of the shaft, we would have to sum that to 0, right? Otherwise, there would be an acceleration which would not be constant speed, okay? So I'll say that's constant speed, and that helps to simplify the discussion just a little bit. Do a little bit more background here. Every place where we have a transition from one part of the shaft to another part of the shaft, let's say that each of those places has a fillet, and that fillet has a radius value of 0.04 inches. Okay, this is important because if you don't make those fillets large enough, then what happens? What does it create? A stress concentration. Well, there's a stress concentration generated actually either way, no matter how you do it. But the larger you make that fillet, the more you mitigate that particular effect, right? You decrease that effect of having a stress concentration the larger you make that fillet, okay? If you have a perfectly sharp corner right there, then in theory, what that does is it creates an infinite stress concentration. In practice, it doesn't turn out that it's necessarily actually infinite, because generally in practice, infinite kind of doesn't happen. But in theory, that's kind of the direction it goes whenever that radius value gets really small. All right. Let's say that this thing is made out of 1144 steel. And just to kind of help us out there, I've mentioned where you can find the properties for that 1144 steel. All right, in the back of the book, page 1051, table A22. All right. I'm saying here that it's got a surface that would be most like a cold-drawn surface, okay? And I'm trying to do this very carefully so that I don't confuse two different ideas that can happen whenever we're looking at this kind of thing. Cold drawing something is a process. It's a manufacturing process that is used to apply cold work to a material, and it will change the process or change the properties of that material if you cold draw it, right? It basically can increase the strength by that property. We are not using this statement right here to say that this is necessarily cold drawn. We're instead going to, just look at this information for 1144 steel. What I'm saying is that the surface that happens whenever you do a cold drawing process has some particular characteristics to it. It looks a certain way whenever it's been cold drawn. And we care a lot in terms of fatigue problems. We care a lot what the surface is like, the outer surface of a part. And why is that? Why is it that we care about what the surface looks like on the outer surface of a part? Yeah. Yeah, that's where cracks initiate, right? It's typically on the outer surface of a part. And so especially in the case of fatigue type of questions where the process of fatigue generally involves you stressing something one direction and then the other direction, and then the first direction, then back again. And what that does is it tends to open and close little micro cracks that might be on the surface of a part. And so it really matters a lot to us what that surface looks like, because it gives us a clue as to how many of those micro cracks might exist on the surface. And the more micro cracks and the more severe that they are, that gives us a larger number of sites where fatigue type of processes might initiate, right? And so that's something that will increase a body's susceptibility to failing in fatigue. If it's got a rough surface, typically it is more susceptible to failing in fatigue. So anyway, that's a long discussion there, but I wanted to mention, why does it matter that I'm saying that the surface is cold drawn, right? And how does that differ from actually saying that the material itself is cold drawn, okay? So there's that. We're going to, this is just giving you a little assumption that we're going to use to help simplify it a little bit. Let's treat these belt forces, the 70 pounds and then whatever value of F is that we're going to find here in just a second. We're going to treat those as if they are in plane, even though it looks as if they are not, all right? So this is one of those things that in practice, whenever you're doing calculations, it is often an engineer's job to decide what sorts of effects are negligible, right? And typically when I give you homework problems to do, I usually give you enough clues, and they're usually not that subtle, right? Usually I tell you this kind of stuff. Hey, treat these as if they're in plane, right? What that basically means is that kind of going to ignore the slope effect of that force right there. We're going to look at as if that 70 pounds is applied perfectly vertically, let's say. Okay. I just want to make mention of that, though, that in practice, when you're an engineer, you're a practicing engineer, that's your job to figure out, is that effect negligible, or is it something that I need to consider, right? And over time, you can, you can get more and more comfortable with making those kinds of decisions. A lot of times it involves you having to evaluate things the hard way, and when you get to the end of it, you see that there's a minuscule difference in what effect you had relative to making some sort of a simplifying assumption. So that's a simplifying assumption that we're going to apply in this case. Next, I'm saying that this is all happening at room temperature. Why does that matter? Okay, material properties might vary with temperature, and specifically fatigue effects are sensitive to temperature, right? And so we have some ways that we can correct for endurance limits. You might remember the term endurance limit. Endurance limit is basically the amount of stress that a material can carry and essentially be able to last as many cycles as you want to apply to it at this stress level that's generally lower. It will always be lower than the failure stresses like the yielding stress or the ultimate stress. Okay, so there's this endurance limit, and that endurance limit is affected by what that temperature might be of the material that's being stressed. All right. Then we have 95% reliability. Why is that something that you might need to know about? Why is that a piece of information I might want to give you? All right. Remember, fatigue is not a deterministic process, and yet we are treating it with a deterministic method here. Okay. This is actually okay to do if what you're trying to do is basically design, and you're trying to kind of come up with some barriers that help you know where the limits might be of a particular design. Like you're trying to figure out, in this case, what we're trying to do is determine a factor of safety against fatigue using ASME elliptic. We're going to do this with these deterministic methods, and yet the process itself of fatigue is more stochastic and not as deterministic. That means that even though we might come up with, a particular size of a part and say, this is how big I think it should be, and it won't fail, well, all we're doing really is we're saying most of the time it won't fail, right? And what we're saying here with this 95% reliability is that we actually are going to estimate that 95% of the time, if we had a factor of safety of 1, then it would actually not fail in fatigue, right? And where that comes from, and I won't spend time and pull it up here, but the tests on fatigue are not deterministic. You might have two specimens that by all you could tell they were exactly the same, and you test them both in fatigue, and one might last a large difference in the number of cycles that it might last relative to another specimen that you, by all appearances that you looked at, you thought they were the same, and yet when you put them in a fatigue tester, one specimen might turn out with a very much different number of cycles than the other one before it failed. Okay, so basically that all goes back into discussions that we had whenever we were in chapter 6, but that's why that is an interesting thing. And we're supposed to find the factor of safety against fatigue using the ASME elliptic criterion. All right, so there's a couple ways that we can approach this. One way that we can approach it is we can flip back into chapter 6, and we can find equations that we had for ASME elliptic criterion back there in chapter 6. I might even mention the page number here real quick. There were all these tables, right? So like table 6.8 on page 316, for instance, it has equations listed there for the ASME elliptic criterion. All right. What I'm going to tell you right now is that we are not really departing from these equations in chapter 6. What I am going to show you is that they reformulate these equations for the specific case of shafts way over on page 361. Okay. On page 361, actually I guess it starts on 360, but it does it for several different failure criteria. And there's an equation there for the, it says DE-ASME elliptic. What does DE stand for, you think? Distortion energy, right? And so that basically refers to what is the methodology of trying to combine the different kinds of loads that come together on a problem like this. So real quick, conceptually, what kinds of loads are applied to this shaft, would you say? Okay, it definitely has a torsion that is going to transmit between those two pulleys, right? As well as what? Okay, if it's rotating, which we're assuming it is, then what happens? Okay, it's being flexed and rotated at the same time. Okay, so it will have flexure, but that flexure is going to lead to a bit of a fatigue problem, right? Because as you're flexing it, you're rotating it, and so if a patch of material is here and you're flexing it down like this, it's going to be experiencing tension, right? But you keep flexing in that direction, and yet the specimen rotates, the shaft rotates, right? And so once it rotates and that patch is down here and you're still flexing it down like this, right? Well, what does that mean? Okay, that patch will now be experiencing compression. So what you have is this cyclical loading where it has tension, compression, so on and so forth. And so what we're doing here is we're having to combine that effect with the torsional effect potentially for a particular specimen. And if you remember, there was actually a portion of chapter 6 that dealt with combined loading. Do you all remember that? Okay. It uses, in that section where it gives you those equations for combined loading, it uses the distortion energy criteria to do that combination. And so that's why each of these is labeled as like DE-Goodman or DE-ASME elliptic, right? It's mentioning that it's using the distortion energy criteria, which is covered in chapter 5, right? It's using that to do the combination of the two different kinds of stress, the shearing stress due to torsion, as well as the flexural stress, and it's using the distortion energy criteria to do that combination. All right, and what you see there is that there's two different formulations of the DE-ASME elliptic criterion. One of them, it doesn't exactly have it solved for factor of safety, which is letter N. Okay, this is again on page 361. It doesn't exactly have that formulated in terms of N. Instead, it has it formulated for 1 over N. Okay, well that's close, right? So I'm going to actually use this as my guiding equation for everything else that we do in this problem. And I'm just going to go ahead and write it up here real quick. This is the equation. 1 over N equals 16 over pi d cubed. Okay? And what you're seeing with that particular, that a lot of you might look at that and go, man, factor of 16 and pi, and what? Why are those things in there? What you're doing is you're actually incorporating equations like TC over J or MC over I, the flexural stress equation and the torsional stress equation. You're incorporating those into this equation so that they're built in, because those are the types of loads that shafts tend to always carry, torsion and flexure. And then sometimes they might also carry an axial load as well. All right, so that's where that particular number comes from. And this gets multiplied by 4 times K sub F. What's that? Okay, K sub F is a fatigue stress concentration factor. All right? And that's something that you may remember that for fatigue, we don't use a theoretical stress concentration factor because it turns out that in practice, stress concentrations don't seem to be as severe as the theoretical stress concentration might predict when you're using it in the context of doing a fatigue problem. And so there's a method that we use to basically reduce the value of that stress concentration so that it's appropriate for fatigue type situations. And we do that with something that's called the notch sensitivity factor. Okay, do y'all remember that? There's a Q factor that goes in there, and you reduce from the theoretical stress concentration down to a fatigue stress concentration. Okay, so that's what the K sub F is there. M sub A, I'm actually going to punt that for just a second. I'm going to talk about that here in just a second. So I'm talking about that momentarily. S sub E, what's that? Okay, that's the endurance limit. All right, I mentioned that just a minute ago. Okay, and those same kind of factors are in other places here. So S sub E is still down there. K sub Fs, all right, same idea, but for the torsional aspect, the shearing aspect, right? That can be a different number than the flexural aspect. And then we have this T sub A. All right, so that actually lets me have a couple of things I can talk about at the same time. M sub A and T sub A. All right. M sub A and T sub A are bending moment and torque that are being applied in a particular shaft, and here's how you should interpret those values. This is not exactly here's how I would say it. Let me actually say it the way I would say it. This is the bending moment that causes an alternating stress. Okay? It's not exactly an alternating bending moment. Right? So I want you to interpret that value, the M sub A. What that means is that sometimes in a shaft, you're going to have a bending moment that causes an alternating stress. Okay? And so that's the bending moment that we're talking about here for M sub A. Right? Over here for T sub A, what do you think that is? It's a torque, right, that causes an alternating stress. Okay? What do you think the next couple of pieces are? It's probably going to deal with a mid-range stress. Okay, so K sub F, M sub M. That's a bending moment that causes a mid-range stress. Okay, and then S sub Y. And this is all going to be squared. And then here we have 3 times K sub Fs, T sub M over S sub Y. Okay. This ASME elliptic criterion uses that S sub Y. That's our yielding strength for our material. It uses that because what you're doing with the ASME elliptic criterion is you're trying to do something to account for first cycle yielding, right? All in one kind of criteria, right? Without having to do a separate criteria. It gives you a smooth, continuous criteria that you don't have to do 2 separate things to evaluate first cycle yielding as well as the fatigue stuff. Okay, it doesn't do it perfectly, as in it is not conservative. It is not. You could end up being in a particular position on the failure locus where this particular method would not predict failure, where you would in theory predict first cycle yielding. So that's not necessarily great, but it is nice that it is a one-stop shop. It kind of encapsulates it all in one process. All right, so that's our equation that we need to work with. Okay, what things in that equation do we know right out of the gate? Yes, sir. Did I not square root it? Yeah, so he's basically saying that I should have put a to the 1/2 power right here. Thanks for catching that. Okay, so I have the square root of all that stuff, which is good. It's a good thing you caught that, because otherwise I don't think we would have had consistent units that would have actually given me a factor of safety out of all of that. So, all right. So, as you look through the variables, this is, ultimately what we're trying to find, what we're asked to find here is the factor of safety. That is N. That's what we're trying to find. Okay? What all do we know already in this equation? Okay? We do know the diameters, right? So at any particular position of the shaft, it's not that hard to come up with this D. Okay? Awesome. So that much we feel good about, the diameter. What else? Do we know anything else? Okay, we can easily find the yielding strength. Okay, and y'all know how to look those things up, I assume. I don't think I'm going to spend a lot of time on that. Let me just give you what that value might be. Let's see. Got to find it here. All right, 5,200 psi is what I have here for yielding strength. Okay, so let me just put that up here. S sub y is equal to 52,000 psi. Okay, the other thing that is another property we're going to need in just a second is what? Okay, in order to find endurance limit, we actually have to go through a process to find that endurance limit unless it's directly given for some reason for a certain type of material. That process generally involves correcting an endurance limit for all the factors that we have to take into consideration. Okay? And so, but with all that whole process, we usually start with S sub UT. Okay, the ultimate tensile strength. And so I'll go ahead and give us that as well, the ultimate tensile strength. Kind of jumping ahead here just a little bit, so I got to find it. Let's see. 93.7 KSI. All right. So those are some things that that will help us find S sub B, but those are not S sub B directly. I would basically say that we have work to do in each of these quadrants, right? Each of these different items that I have to find here, I have to do some work to figure out what those values are before I plug them into this equation. Okay? So, what would you like to start with? Okay? I like that. So that's probably maybe the most tricky part of this and the part that may be different than what you've already seen. Not much different, but you know, it's probably the part that involves the most thinking. And so let's go ahead and do that. So alternating moment, or the moment that causes an alternating stress, torque that causes an alternating stress, torque that causes a mid-range stress, moment that causes a mid-range stress. These are all things that we need to find. What do I need to do to get those? Okay, I probably need to find these reactions, RA and RB, that is shown on this body up here. Before I can find RA and RB, what else do you think I might need to find? F. Okay, I need to find F before I can find R sub A and R sub B. But that part, fortunately, isn't that hard to do. And the reason it's not that hard to do is you can see here that we know this radius right here is what value? 4 inches. And this radius right here is what value? 1 inch. Okay, which means I can do a sum of moments around the axis of this shaft, and I can figure out what F must be. Okay, so summing torques or moments around the axis, and what I find there is that I will have 70 pounds times 4 inches in one direction, and then I will have F times 1 inch in the opposite direction, and those should sum to 0. Okay, which tells me here that F has to be what? 280 pounds. Okay, so I was basically using my equilibrium equation around the axis to figure that out. And it is important that I look at this and say, oh, it was turning at a constant speed That's why I could use a static form of that equation, right? If it wasn't turning at a constant speed, then there may be some need for you to figure out dynamically what was going on in there. But first, you know, we'll keep it relatively simple here at first. All right, so F is 280 pounds. Now what? Okay, we might want to take a moment around, let's say, point A. Okay, and if I take moments around point A, then what I have is 70 pounds times 9 inches. Okay, and that would be in the counterclockwise direction. Then I have F, which is 280 pounds. That would be in the clockwise direction. How far is that from point A? Okay, 24 inches. And then I have R sub B, which is going to be 34 inches. All right, and this all is going to sum to 0. Okay, and if I solve then for that, then what I end up with is that R sub B is going to be 179 pounds. Okay, then what? Slide this. Yeah, so then you can sum, if you want to, you can sum forces in a vertical direction. And you have minus RA plus 70 pounds minus 280 pounds plus 179 pounds equals 0. Okay, and this allows you to find RA. All right, and RA turns out to be negative 31 pounds. What does the negative mean? Okay, yeah, when I drew these arrows on here for the reactions, it doesn't look like it would be wrong necessarily, right? It's reasonable enough to guess that those would be the directions that the reactions go, but it turns out that that RA actually pushes upward on the shaft at point A rather than downward. Okay, so I need to either deal with that by keeping that arrow the same direction and always using a negative value, or in subsequent steps, if I use that information, I need to remember to flip it around if, you know, I want to show it in the actual direction that it goes. Okay? Good job. So now we've got our reactions here. We'll put them on here. RB was what? Let's see, 179. RA is negative 31. And F is 280. Okay, what do you think might be next? Okay, one way that you can do this is by doing a shear and bending moment diagram. All right, because with a shear and bending moment diagram, the ultimate piece that comes out of that is the bending moment. And that's what we need up here for M sub A. Right? So what would a shear and bending moment diagram look like for this body? Okay, tell you what, I'll draw it again. I'll draw it like this. And I'll draw it with the elements of force that are applied to it actually shown in the correct direction. Here I've got 31 pounds. I've got 70 pounds here. I've got, let's see, 280 pounds here, and I've got 179 over here. All right, and what do I do with that? Okay, well, let's set up some graphs. Okay, first one up here that I'll do is a shearing diagram. All right, so let me just do this like this. And what we'll see here is that we are going to increase from 0, right? There's 0 before there's a shaft, right? You get to the shaft, and the very first thing you apply on here is an upward 31 pounds. So that takes you up like this. Whoop. Then what? Okay, the next change we have occurs at the next applied force, right? So it increases there by 70 pounds. This may not end up being drawn perfectly to scale, but hopefully you get the idea. So this is 31 right here. It goes up to, okay, 101. Okay, and then it drops by 280. Which should take you down to negative 179. And then back up to 0 here. Okay, so this is my shearing diagram, and that's going to be in pounds. All right. Now, by looking at this diagram, where do you feel like the worst case scenario is going to be for bending moment? Okay. Yeah, so where we're going to look at probably is where the smaller pulley is. Okay. The reason why you can kind of tell that is that this shape of the bending moment diagram, you know, it'll have a particular slope like this. That slope increases here to go up to some other location, and then you have a negative slope that comes down to the end. You know, you can tell more or less just by looking at the shear diagram that that's going to be the general shape of the bending moment diagram. Would you agree with that? Okay, and so you see here, this is where we have our maximum bending moment occurring. All right. And since I didn't give you any information about how wide the gear was, that smaller gear or smaller pulley, I didn't give you any information about how wide that was, we're going to pretend like it's 0, right? We're going to pretend like it's really no difference left and right, you know, as far as the bending moment value is concerned. That's not always the case. In some cases, especially if you're dealing with shafts where the components themselves are large relative to the length of the shaft, it may be important for you to actually look to the left of the component and actually look at the location, you know, to the left or to the right of where the component is being installed and find the bending moment at those locations. But for us, we're going to pretend like that's negligible. Okay? Now the question I have here is this. Just because I found my maximum bending moment, does that necessarily mean that I found my worst place in terms of stress? I'm taking very, very generally now. You know, in all cases, when I find my maximum bending moment, does that always mean that I have found my location of maximum stress? Okay, not always, right? Because what's another factor that matters? Shaft diameter. Okay, if you can have a lot bigger bending moment and still be okay if you have a very large shaft, right? Or a very large component of any kind. Generally, the larger you make it, the less it's going to have stress in it. And stress is going to be the thing that causes the failure, not just bending moment, okay? So a good thing that we need to do at this point is, well, I guess one of the first things we need to do is actually figure out what this bending moment value is. But it is a good idea for us to have in our mind, where is our critical location, okay? This is kind of a mental discipline I want you guys to start feeling comfortable with, is how do you figure out where the worst case scenario is for a particular body. All right? So let's think through that. How do we know where the worst case scenario is? Okay? Well, one thing we can do here is we can say we know where the worst bending moment is going to be. And how do the diameters compare with one another? Okay, the right side and the left side, the right end and the left end are the same size, right? And so I would basically look at this and say, well, if I have a problem at point D, right, to the right in this small little piece right over here, well then my problem should be less severe than that at point C. And the reason I know that is that my bending moment is smaller, right? Those are the two factors that matter to me, is the size and the bending moment, right? And they're the same size, either to the right of component D or to the left of component C, right? Those are the same size, and at location C it has a smaller amount of bending moment. So that lets me say, I don't need to consider this right here, because this is going to be a bigger problem all the time. Does that make sense? Okay. Another thing that I need to probably say here before we go too much further is there are two effects that we're trying to account for. One is flexure and one is torsion. All right. So a quick question here, where does torsion exist in this shaft? Where does it carrying torsion? Okay. Yeah, in this little section right here, it is transmitting torque. Why is it not transmitting torque in segments AC and BD? Yeah, those bearings, and it says up here, lossless, right? We're assuming those have essentially zero torque that they are applying at those locations. Okay, so that means that in this segment right here, we are carrying torsion in addition to flexure. All right, that means that segment AC and segment BD are in the same scenario as each other with respect to what types of load they are carrying. Okay, so that again provides us a justification and some faith that we can go ahead and say point D will always have a worse problem before point C does for this particular problem, right? Everyone agree with that? So it allows us to eliminate one location that we would have had to evaluate as a potential critical location. If that diameter between A and C had changed, that gets thrown out the window. Like, what if I all of a sudden said this was not 3/4 inch diameter, this is now 1/2 inch diameter? Now you don't have the logic in place to prove to yourself that you're always going to have a worse problem at D than you have at C. Does that make sense? So I'm trying to give you a little bit of an example, what you can work through mentally to know where your critical location might be. If you can do this, then it allows you to eliminate certain possibilities sometimes and decrease the amount of work that you have to do. The reason why is that that's, what causes something to have a worse case in terms of stress is not just the bending moment, it is bending moment combined with size, right? Because it's MC over I, and C and I, those two values in the flexural stress formula, C and I, those are both functions of how big the shaft is, what the diameter is of the shaft. And so that's why, because those two sizes are the same, AC and BD, that allows me to do some logic there and say, I know that it must be D that would have the problem first. Okay? All right, so there's, we dealt with it to the right of component D and to the left of component C, and we're saying it's always going to be there to the right of component D. What about in between? Like to the left of component D or to the right of component C? Do we know which of those is going to be a worst case? Okay. Well, let's think about it. Do they have the same amount of torsion applied? Okay. same value, right? They're going to be opposite direction in order to put the torsion in there, but they're going to have the same value of torsion. So that's kind of a moot point, right? That's not going to change it being one location versus the other, because they're going to carry the same at those two locations. All right, what about flexure? Okay, well again, we have size that matters, and we have bending moment that matters. Okay, what's the bending moment at point C relative to point D? Definitely less, right? And so for the same type of logic that we used before, we can say we don't have to think about the location to the right of the component at C. We know that it's going to occur, if there's going to be a problem, it's going to occur right there. And so between all of the different locations that would be potential critical locations, I've now eliminated two of the possibilities. Is there any way for me to figure out between these two which of them is in a worse case? Okay. And the answer isn't necessarily yes or no, right? I'm not saying that you should be able to say yes or no just yet. Okay, let's think about it. So it is definitely, they carry the same amount of bending moment between those two locations, right? So there's that. But then one of them is smaller, right? But the one that's smaller is not carrying torsion. So there's the bigger one, but not only does it have to carry the flexure because of the bending moment, it also has to carry, the torsion down the axis of this part, right? So what I'm trying to point out here is that we're in a situation where logic doesn't allow us to inspect this and know whether or not it's going to be to the right or to the left of component C. Okay? Which means that for the rest of the problem, we're going to have to evaluate two different locations, right? At least to the point where we do have some basis to eliminate one of them. All right? So let's actually get to some sort of a stopping point here by determining what this value is. We've basically said we don't need to worry about this value down here. We do need to know this value right here. How do I know what that value is? Okay. There's this area right here. If you know that area, it tells you what the difference is between the starting point and the ending point of that little segment, right? And so that area is going to be 179 times what? 10 inches, right? So 1790 inch-pounds. Okay, and that's what we have right there. And so what we have now determined is one of the things that we cared a lot about, and that is what? Okay, we have a bending moment. That was in this equation up here, right? Now, we actually have two bending moments in this equation. We have a bending moment that causes an alternating stress and a bending moment that causes a mid-range stress. Okay? Where should we plug this value in? Okay? We have a vote for alternating. Okay? We have one person who says, we probably want that right here. Okay? Who agrees? I see several hands. Who says, nope, that doesn't look right? Who says, I really don't want to commit right now? I'm going to plead the fifth. All right? Pretend like you're in the U.S. government and you don't have to answer questions. All right. So you're right. That is going to be, it's going to create an alternating stress. Okay? The reason it's going to cause an alternating stress is that this thing is both rotating and bending at the same time. Right? So it's in that scenario that I described a few minutes ago where there's a patch of material, and because it's rotating, that flexure that continues in the same direction will cause that same patch of material to go from a compressive to a tension to a compressive to a tension and so forth. Okay? Now, question is there anything that I can do to figure out what M sub M should be? Okay? Someone says it's 0. Do you agree? Okay? Yeah, it is going to be 0. The reason why is that flexure that happens in there is going to alternate between, you know, negative and positive of the same number, right? It's going to basically go from a negative stress to a positive stress to a negative stress to a positive stress, and it's going to be the same value. Another word for this is fully reversing. Okay, so there's that. What about torques? Okay, all right, so the torque that exists between point C and D, that's the only place that torque exists at all. The question is, does that torque change? All right. Does it pulsate? Is it one of the words that it uses sometimes in the book is a pulsating torque? And the answer is not for this problem, right? For this problem, it's inputting torque on one end, taking it out on the other end, and so the torque that's being transmitted is going to be 280 inch-pounds, and that's going to come into T sub m right here. And T sub A is going to be what? 0. All right. We're actually, further along than you might think. S sub Y is 52,000 psi. 52,000 psi here. And so what we have left to do is we have left to find the endurance limit, the fully corrected endurance limit, as well as these stress concentration factors. Okay? Basically, we have 3 things left to find. So continuing on, what we'd like to continue to do here is find these last few parameters, the fully corrected endurance limit, and our fatigue stress concentration factors. So I think what I'll do next here is I'll give myself a little bit of room, and we'll find that fully corrected endurance limit. All right. So let's see. SE, we remember this from chapter 6. Kind of our starting point with our fully corrected endurance limit is that we have kind of our starting point with that, the uncorrected one, times a number of constants. So Ka, Kb, Kc, Kd, Ke, and I think they maybe even had a Kf, and each of these had some kind of a meaning. So A was the Ka was the size factor, excuse me, Ka was the surface factor, Kb is the size factor, Kc was a loading factor, Kd was a temperature factor, E was a reliability factor, and then F was kind of a miscellaneous effects factor, which kind of something you apply if you have some sort of special data about a special situation. It gives you kind of a placeholder here where you can apply even more factors. These are called Marin factors. All right, SE prime, remember we found that by basically taking 50% of the ultimate strength, because that's roughly what the kind of the ideal situation with the fatigue testing gave us, is that it's roughly about half of what half of what the ultimate strength was gives you that uncorrected endurance limit. Okay, so let's just start with Ka. And this again is the surface factor. Up at the very beginning, it told us that the surface was similar to that of a cold drawn kind of a surface. If we look into the table in the book, there is a table 6.2, and it gives us a couple of different values that we can plug into an empirical equation to find Ka. All right, and those values are 2.7. This is specific to a cold drawn surface, so these numbers might change if it's a different kind of surface, but 2.7 times 93.7 is the value of the ultimate strength in KSI. That's what it's expecting into this empirical formula. And then that gets raised to the negative 0.265. Okay, and if you plug all of those in, then that surface factor value ends up being 0.8107. Okay, and I'll just write over here, look at table 6.2 in the book. All right, so there's one of our values that we might care about. Next, we have a size factor, KB. Okay, now the reason that we need a size factor is that, remember, these fatigue processes are not deterministic in nature, they are stochastic in nature. And so the larger amount of material you have that reaches high levels of stress, the larger number of potential sites that you end up with where you could initiate fatigue. And this factor basically takes that effect into account. It does give a little formula in the book for this, for round, rotating, bending type of things, which is exactly what we have, so that's nice. And we need to do it actually for two different sizes because we have both a 1-inch diameter. Okay, that's to the left of this component where we're trying to evaluate this. And the value for that is going to be KB is equal to 0.879 times, okay, that 1 inch we plug in here. We don't plug in units because it's an empirical equation. And then we take that and we raise it to negative 0.107. Okay, and when we plug that in, we end up with just 0.879. Okay, now for the 3/4 inch shaft, it's basically the same thing. KB is going to be equal to 0.879. The only thing we change is in here. We put in 0.75, and that gets raised to the 0.107, negative 0.107. All right. So then that ends up giving us 0.9065. Okay, and it does make sense here. This value is supposed to decrease as the shaft becomes smaller and smaller, so that is going the right direction. Okay, so now what we want to do is we want to look at these other factors. So we'll go to K sub C. Okay, this is a loading factor. All right, now when you are doing a combined loading type of a scenario like we are here, meaning we don't just have bending, we don't just have torsion, we don't just have axial, we have a combination of both torsion and flexure. And those equations that we use, this DE ASME elliptic equation that we started with up there, takes that into account, uses this combined loading type of a formulation. And it tells you in chapter 6 that when that's the case, you don't use this loading factor. I'll say don't use. We used DE formulation instead. to combine our different kinds of loads together. Okay? So we don't use that one. Next, KD. Okay? So K sub D is the temperature factor, and we will say, since we are at room temperature, say temp factor here. I'll say since we're at room temperature, that means K sub D is going to be equal to 1. Which is the same thing, I guess, as saying that we don't use that one either. All right, next we have K sub E. Okay, K sub E is the reliability factor. All right, that reliability factor is a matter of just looking that up out of a table. And so we see here table, let's see, 6.5. Okay, and in table 6.5 you can just look up a 95% reliability, and it will tell you that K sub E should be 0.868. Okay. All right, so now we need to put together our fully corrected endurance limit S sub E. Okay. S sub E is going to be equal to S sub E prime. S sub E prime is just half, so I'll put 0.5 of our ultimate strength, which was 93.7 KSI. Okay, to this we multiply all these Marin factors. So we have 0.8107, we have 0.879, we have, and that would be for, keep in mind here, we actually have to do this 2 different times. So I'll say this is for the 1-inch shaft here is what this formulation is going to be. So 0.879, KD is just 1. You can either write 1 explicitly if you want to, or you can just leave it out. And then here we have KE would be 0.868. Okay, and when we put all this stuff in there, what we end up with is 28.98 KSI. Okay, next we've got S sub E for the 3/4 inch. Okay, and it looks very similar. The only thing that's different is we change the size factor. So this all this stuff stays the same. And the size factor goes to 0.9065. But everything else stayed the same. All right, and when we plug all these in, we end up with 29.885 KSI. All right. So that is the fully corrected endurance limit S sub E. We're getting real close now. Now we need to do our fatigue stress concentration factors. And so what I want to do for these is, keep in mind the process is you find a theoretical stress concentration factor first, then you apply a notch sensitivity to that and kind of correct that a little bit to find K sub F. And then that's what we need. So we'll start over here. I have some charts way up here at the top. And I'll tell you what, I'm actually going to start with the first chart up here for the case of torsion. And ultimately what we're going to try to find with that is K sub Fs. Okay. Now, what you need on this chart is you first need to know what is your capital D over D. Okay. Well, to the left position on this shaft, this is actually pretty easy because the size of that part right there was 2 inches, and it's 1 inch to the left, and right, so that basically means that this is going to be 2 over 1, 2 inches over 1 inch, which is just 2, and that means that we are on this curve right here. Okay, so that's if we're to the left. Let's just deal with that one first. What about R over D? Okay, R over lowercase d. So the R that we have there is the radius, and that was again provided over here. It says all the different transitions are filleted with radius values of 0.04 inches. Okay, so that means 0.04, for at least for this first one that we're dealing with, is going to be 0.04 over 1, which is just equal to 0.04. If we look along here, 0.04 is likely to be somewhere, let's say, right about here. We read up to this location, and then we read that over to here. And you can't get super accurate on these. One thing we can notice is that's 1.8. This would have been 2.0 at that line. Halfway in between would have been 1.9. It actually, I may not have drawn this perfect. It probably winds up a little bit lower than that. Let me just say that coming out of here for the left portion, this is just going to be equal to 1, I'll say K sub TS. That's what we're finding here. That's the theoretical stress concentration factor for the shearing induced by torsion. You can tell here this is showing you that's a round part experiencing torsion. Ends up being about 1.85. You can't get these super duper accurate if what you're doing is using this chart method, but you can have a pretty good estimate for what that value should be. So I'm going to say it's about 1.85. Okay. So now the next question is, well, what about the one that's to the other side? Well, the one that's to the other side, we end up with a D over D. I'll just write it over here. D over D ends up being 2 over 0.75. Okay. And that ends up giving us a value of 2.66. And that actually goes outside of these curves that we have available to us on this chart. And that brings up a good question. I did this on purpose so that I could answer the question of, well, what happens? What do you do if you end up outside of the chart? And I think, to me, one of the best things to do if you end up outside of the chart is just realize that these curves are getting closer and closer together as we move, as those values move higher and higher. If you end up outside of the chart, just kind of pretend like you're on the outer limits of the chart and use that as an estimate. And, if later on you want to doubt your results a little bit because you knew you did that along the way, that would be completely fine. But, this is a good way to deal with it. All right, so there's that. But then the other question is, what about R over D? Okay, R over D ends up being 0.04 over 0.75. Okay, and so that value ends up giving me 0.0533. Maybe I'll drop that below here. 0.533. Okay, and so what that does, we'll change the color here a little bit. It ends up that I'm just barely to the right of this location, still going up and reading to this point on the chart, and reading over here, something like this.
And I would actually say that that's probably, with 1.4, 1.6, 1.8. In the middle there would be 1.5. I'd say that's about 1.55. Okay, so here the other K sub TS is equal to 1.55. Now, it just kind of occurred to me just now, I probably won't even need that value. And the reason I won't need that value is this shaft is not actually carrying torsion over on that side. It's not carrying torsion over there. So I showed you how to do it. I'll probably go ahead and leave that in the video and everything, but we may not end up actually needing that value. All right, let's continue on. That's finding the theoretical stress concentration factor for the case of shear. The next thing that we've got to do is take that, here we go, this is the chart that I was looking for. This is in the case of shear, this is finding notch sensitivity factors. And this is kind of the easy way to do it. It actually works pretty well as long as you don't need a super accurate result. There's another way that you can do it using a Neuber constant and such. And if you look in chapter 6 around where this chart is published, then you will actually see how to apply that and maybe get an even tighter value for Q, but I'll just show it this way here. All right, so first of all, what's our notch radius? Well, that's actually pretty easy. We're right along here. Okay, and we read up. We're actually not far away from a 100 KSI value for our strength, our ultimate strength. That's what each of these are, is your ultimate strength. And so that tells me that my notch sensitivity will be about 0.8. Okay, and they call that in the book Q shear. Right. All right, well, what do I do with that? Well, the equation that we use with that is of the form that K sub Fs is going to be equal to 1 plus Q that we just found, which is 0.8, multiplied by the K sub Ts that we found up here. Okay, that was way up here a second ago. K sub Ts was 1.85. And then that gets, we subtract 1. All right. And if we plug all of that stuff in, then K sub Fs winds up being 1.68. Okay. And that's our fatigue stress concentration factor for the case of torsion. So 1.68. Now that we have that, let me go ahead and make a note of that way up here where I've been showing this equation. We've been building this equation up, right? So we put that in for K sub Fs right here. That would be 1.68. Okay. And if we need it over here, it would be the same thing, right? K sub Fs over here would be 1.68 as well. All right, so now we just have one more thing to do, and that is find K sub F. And we'll actually need to do that for two different cases, right? We'll have to do that for the portion of the shaft that's to the left, as well as the portion of the shaft that's to the right of that smaller pulley. All right. Fortunately, though, we actually have very similar parameters in these two cases, and so we don't have to find those again. We still know that D over D value, R over D, and such. So, one thing that is a little bit different, though, is that when I draw this line at about 0.04, which goes up like this, you'll notice that we don't necessarily land directly on any of these curves, right? Because our capital D over D that I'm looking for is 2. We have 1.5, and we have 3. Okay? Again, there's different levels that you can do this. I'm going to show you kind of the quick way to make an estimate, right? I think of this as, you can think of dividing that 1.5 difference between one of these locations and the other location. Okay, we can think of dividing that up into basically 3 chunks, so that I would have 1.5, 2, 2.5, 3, right? And that gets you close enough, right? You make an estimate there. You say that puts you right about here. Okay, this would be 2.2. Right here would be 2.4. And so I'm going to call that right about 2.3. Okay. All right, and once I know that that's 2.3, I'll say that that's our K sub TS. Not K sub TS, just K sub T, I mean. This is going to be equal to 2.3, and this is for the 1-inch side. What if we look to the other side, right? Well, the other side, remember, we had a slightly higher than 0.5, right? That sets up a little area right in here. And we had a capital D over D of 2.66, which is, not far different from about a, it's a little bit more than 2.5, but I'll kind of use the same technique here. I'll take this and I'll split it into roughly thirds. Something like that. And it looks to me like we wind up being pretty much about 2.2 when I say that that's probably pretty close to my 2.66 value as far as capital D over D. Okay, so K sub T is 2.2 for 0.75 inch side. Okay, well, what do we do with that? Well, it's very similar to what we did before. We go to the notch sensitivity chart that we have right here, and we're going to look at a notch radius value of 0.04, and we'll read right up to where, it might be a little bit below that 100. Okay, and we'll read over may not have drawn that super straight, but I think we wound up probably not too far off. And I'm just going to say that this is going to be close enough to say that this is 0.75. Okay, well, once I know that that is 0.75, the process of finding K sub F is the same as we did before, same structurally anyway. 1 plus 0.75 times, and again, let's start for the 1-inch portion of the shaft. You have the 0.75 times, and here we put in a 2.3 minus 1, because remember that 2.3 was the value of K sub T for the 1-inch portion of the shaft. And when I plug this in, that ends up giving me a 1.975. Okay, what about for the 0.75 inch part of the shaft? Well, it's again structurally the same. 1 plus, this would be K sub F, 1 plus 0.75 times 2.2 minus 1. And when you punch that in, it ends up giving you a 1.9 for the K sub F. All right, awesome. What we are ready for now is we are ready to actually compute our factors of safety that were requested at the beginning of this problem. So we'll keep these values here in mind, and we'll slide over here. And I'll tell you what we'll do is we'll give ourselves a little bit of space here if we can. Alright, so I'm going to first look at the 1-inch portion of the shaft. Okay, and for that 1-inch portion of the shaft, my 1 over n is going to be equal to 16 over pi times, remember the d there is going to be 1 inch. That will be cubed, although it doesn't really matter other than just make sure the units are correct. This gets multiplied by 4, and then my k sub f value for the 1-inch portion of the shaft was 1.975. M sub a was 1790 inch-pounds. S sub e was, if we look at the 1-inch portion, S sub e would have been 28.98 KSI. Okay. And I mean, sometimes you might need to make sure that your units line up. It might actually be better for me to put this in here as far as this goes with PSI. So 980 PSI, because that's probably going to jive better with the units that I really have there. That ends up being squared plus, how much alternating torque did I have? I had 0. So that term, you know, this term doesn't even show up. The second term in this series doesn't even show up. I also did not have a bending moment, a mid-range bending moment. Okay, so that term won't show up. And so what we'll end up with, our next term is going to be 3 times 1.68, okay, times the T sub m there is going to be 280 inch-pounds. All this gets divided by 52,000 PSI, which is the yielding strength for that material. Okay, all that is taken to the 1/2 power, and when you solve this for n, it tells you that n is going to be equal to 0.803. Okay, and we can interpret that. Okay, the first thing that we think whenever we see a value like that is it looks like the part won't last forever. All right, we are doing a factor of safety against fatigue. When that factor of safety against fatigue ends up less than 1, it means I don't think we're going to have infinite life. Okay, there can be a second phase of this problem where you do evaluate and you figure out how many cycles you think it will last. We won't do that now, but that's, you know, one of the ways we can interpret that value that's less than 1 is we don't think it's going to last forever. All right. But remember, we had 2 potential critical locations. There's another potential critical location on the other side. Okay, in that 0.75 inch diameter section that's over to the right side of that shaft component. The process is really the same there. 1 over n is going to be equal to 16 over pi times, now we have to put in the diameter that's correct for that side, 0.75 inches. This then is going to get multiplied by 4 times, and remember the k sub f that we had there for the 0.75 inch side was just 1.9. Okay. It does have the same amount of bending moment that causes alternating stress, so we put in 1790 inch-pounds. But we do want to use a different value for the endurance limit because we had two different values down here for that. And so we go back and look at that, 29.885 KSI. Okay. $29,885 PSI. And all of that would end up being squared. All right. And then we have to look through for this other side. Do we have any other kinds of loads? All right. We do not have an alternating torque, nor do we have a mid-range torque, because to the right of where that shaft component is, it's not carrying any torque anymore. These are lossless bearings, so there's no bearing torque. And so those terms aren't in there. What about a mid-range bending moment? We wouldn't have that either. Okay, so we actually just leave just that one term in there. And from this we can compute N. And it turns out that N winds up being 0.364. Okay. We can make the same type of a conclusion as we did on the first, the 1 inch portion and say that, well, we know it's not going to last forever, but we can also make a relative comparison between these two and make the statement that this was the critical location. Okay, and so that's the one that would control failure, at least according to this analysis. Well, I hope this has been helpful, and good luck on working the problems that you might be doing with respect to this content. I'll see you on the next video.